So this is one of the topics that we have been working on with the help of Dr. Kobayashi. Homographic imaging. We try to image the interior of concrete using some techniques which is based on the propagation of elastic wave. So this is the conceptual schematic diagram. Okay, when you have this array of sensors attached to different sides of a concrete, and if you propagate or transmit elastic wave, elastic wave is actually a form of energy. You can induce elastic wave by simply tapping with a hammer, for example, on the surface of concrete, and that will give you energy. This energy will be transferred from one point to another point. And if you have receivers, an array of receivers on the other side, this data will be captured by the sensors, and from there you will know the travel time, how long it takes for the wave to travel from one point to another point. So if there is a defect here, we have a certain algorithm, okay, to predict, to visualize the interior, to visualize this defect. So if there's nothing, the wave will probably propagate in a straight line. That means you will get a velocity value which is a normal, that is reflecting the health of the concrete, which is a perfect. If there is a defect, the wave cannot propagate in a straight line, so it will be bent or distorted. So in the end, it will take longer time to reach the other side of our concrete. So based on these principles, Dr. Kobayashi has helped in developing a special algorithm, okay, which is based on ray tracing. Okay, and in this, he implemented the use of a numerical model, the so-called simultaneous iterative, what do you call it, SIRT, simultaneous iterative reconstruction technique, okay, in suggesting the element value for velocity. All the elements will have a certain velocity, and based on that, we can plot the contour. Okay, so this is a perfect example. Because this is a simulation example. It shows that there is a defect, a void at the center of the model can be successfully visualized, okay, using this technique. And we are actually working on developing some algorithms, because this is basically based on the principles of travel time, wave travel from one point to another point. And we find that there are some issues particularly related to the sensitivity, because the velocity is less sensitive as compared to other parameters such as the shift of the frequency of the wave and also the attenuation, meaning to say that the damping effect. So now I have students who is working in developing new algorithms, and we are going to try that out in a few months' time. So this is a practical example of how we utilize this tomography technique. We have a bridge deck. Okay, this is the bridge deck, and from the top as well as the bottom surface, the soffit of this bridge deck, we can see surface breaking crack. Okay, we wanted to know whether this crack are actually belonging to one crack. Actually, this crack, will they actually belong to one same crack? Meaning to say that this crack propagating through the thickness? How do we find that? So we can use this technique. Just simply put 5 sensors on top and the soffit, carried out the tomography. This is the imaginary wave, half of the elastic wave. Then you see these are the results. Okay. So the low velocity region are actually connecting, okay, from top to bottom. So we can come to a conclusion that this actually is one crack penetrating through the thickness of the slab. And another good purpose of employing this kind of a technique is that we can confirm the condition of the interior, okay, after the repair. So you see, this is a good example. After the repair, we do the same measurement again, okay, conduct the computation for tomography, and you see the yellowish or the reddish region has been disappeared. So this confirms the effect of the repair. So this is a very good technique. In particular, it is very appealing, okay, to the customer, to the client, or to those who do not have the necessary engineering or technical background to understand, okay, what is happening. Because this is visualized. If you just show them the numerical values, probably they don't have any image or any idea about what is happening. What are these values telling us? So if you have some sort of diagrams like this, so it will be very appealing to them, and it is very easy for them to understand. Oh, the repair has been successfully done. So this has a commercial value. We are not going to talk about that. Dr. Kobayashi has also helped in developing a 3D model for the tomography. So this is a practical work that we have conducted in Japan, Hokkaido. construction repair work was undertaken, and the authority wanted to know the effect of this repair. So we proposed tomography to them. Okay, and this is a scenario whereby we are working on this scaffolding. We have a system which can accommodate up to 48 channel accelerometers we use. So this is how we generate the wave by using a steel ball hammer. We induce the impact continuously for up to 15 seconds, and then we average all the waveforms in order to get a consistent wave. So this is actually another technique, okay, which we use for the core specimens. We want to see the improvement of the crack. So these specimens were injected with fluorescent liquid under a certain pressure. So okay, these are the exemplary results. So we have 48 channels, and these are the imaginary wave paths before repair, after repair. So 3D is good because we can visualize whatever cross section of desired. So this is the overall, the exterior look of this measurement before and after. You see the yellowish or the orange region has been largely improved. We need to say that the velocity, the general velocity improvement has occurred. So if we want to focus on the status of the midspan, the center cross section, okay, you can also do that. Okay, so this is a result showing a very convincing result showing that improvement by repair has been successfully occurred. Alright, this is another test by tomography. So this is a mechanical test, and this is a very small prism. It is actually a composite specimen. At the bottom here you have normal reinforced concrete, steel bar inside, see, concrete, and then on the top you have the fiber reinforced concrete without any steel bar. So the purpose is to check whether there is any interfacial failure between this concrete and the interface between the FRC and the reinforced concrete. So we carried out the normal load test. It's actually a 4-point bending, and during the load test we stop at certain intervals to conduct tomography measurement. So these sensors are connected by this yellow cable, and it's connected to a system. So we did the measurement at different stages. So the difference is this set belongs to the plain concrete specimens, no composite, and this is the composite one, so FRC and then with LRC. So tomography measurement actually can show, okay, the progressive damage if we carried out at a certain interval. So you see the color is changing, the contour is changing. And then at the final stage whereby you have this critical shear crack failure, you see it's marked by a very large region in red. And the location is well satisfactorily displayed. This is another fundamental test. We cast a block, and on this block we have artificial cracks. Okay? These cracks have varying depth, vertical depth. Okay? The horizontal length is the same. So we attach sensors on 4 sides. This is a specimen showing the cracks with different depths. The measurement, and this is the result of one of the specimens. So you see these cracks have been the location or the depth of the crack can be roughly estimated by the tomography technique. You see if the crack is slightly shallower, okay, the red area is slightly smaller compared to this, which has a deeper crack. So in 3D we can use, we can also cut it into cross section and try to focus on whatever cross section of interest that we want to study. So this is basically the six sides of the specimens, showing how accurate tomography has performed. On top of that, we also did some study, okay, about Rayleigh wave. Okay, I think this morning, for those who have attended the presentation, we use Rayleigh wave to predict cracks, characterize the crack. At the same time, we try to incorporate Rayleigh wave characteristic with tomography. So the hybrid of this is the so-called Rayleigh wave tomography. The good thing about this Rayleigh wave tomography is that we do not have to have at least 2 surfaces for assessment. We need only 1 surface, because based on the propagation of Rayleigh wave, we need only 1 surface of access. lower than the depth of the crack, for example, this is the depth of the crack, the penetration might not be deep enough to be distorted by the defect. So if you plot the tomography out, probably you will get this cross-section view, which means that the concrete is totally sound. You might not be able to detect any defect. But if the wavelength of this Rayleigh wave is almost equal to the depth of the crack, probably you will get some changes at the area where you have the crack. But then it might not be sensitive enough. But if the wavelength, if you change the frequency, by changing frequency, you are actually changing the wavelength. So if the wavelength is greater than the depth of the crack, meaning to say that the penetration of Rayleigh wave is actually exceeding the depth of your crack. So probably the result will become like this. So it can successfully image or visualize the existence of the crack. So these are the uniqueness of, what the special features of Rayleigh wave that we have been focusing on utilizing it. We have these fundamental specimens. It's a deck. Inside this deck you have 4 styrofoam, and these styrofoam were located at different depths. From side A, it was from 30 to 140 mm. And from another side, the opposite side, the depth become from 160 to 270 mm. So this is the location of the crack, and we use 16 accelerometers. These are the arrangements. And the excitation or the generation of the wave basically the same. We use a steel ball hammer effect. So this is the flowchart showing the procedures of the measurement as well as the input of data and the calculation. This is the result. We use 3 types of ball hammer because different ball hammers will generate different source frequency. So for the 3 mm, you have penetration depth estimated is based on theoretical calculation of about 0.11 meter. Then by increasing the size of steel ball from 8 to 15, so you are actually increasing the wavelength, which means that the penetration depth is increasing. So you see, when the penetration depth of the wavelength is small, probably you might not be able to capture the presence of crack, which is deeper than that. But after that, if you change it to a bigger size, okay, the results are very promising. It shows that basically we can use it to visualize all the cracks, okay, up to 140 millimeter. Okay, another example is that we try to utilize this for the actual measurement. We went to a bullet train bridge deck in Japan, and we did the same thing. And this is the result. Actually, these are the results based on the impact test. You just knock it, and then hear, the sound. So the marking are based on the change of the sound. So this is the result. Now, it might not be very accurate. Okay? And this research is actually still undergoing, and we still have a lot of unsolved issues. We are trying to find a balance so we can continue this research. So this is another site project. It's actually a nuclear facility in Japan. So they found a crack there, this crack. And they have repaired it, but they do not know how effective is the repair work. So they asked us to check. Because sometimes the injection of this epoxy or the grout can stop at somewhere in the middle, but you are not actually repairing the whole thing, the whole crack. So it will stop at somewhere because the injection is not sufficient. So it might leave you with this void inside, but nobody can tell whether there is any void. So we try this method. We use the same principles, and this is the result all through, showing that this result probably suggests that the repair has been quite successfully done. Because actually we are using different size of hammers. We are testing it at different depths. Okay. So maybe the repair work is okay, no problem. And before I went back to Malaysia, we had some project also. These are the bridge decks, okay, which has been retired from service. So they cut it and they move it, transported it to a certain research center. And they asked us to go there and do some fundamental testing for collection of data. So we did the same thing, okay? And we also did the measurement on top of the asphalt pavement, the pavement of asphalt, and also at the bottom. Okay, this is the size of the balls, the steel ball hammer that we have, from 5 mm to 35. This will give a different generation of frequency. So we use use this method also to predict the depth of the crack. We have published this paper in ACI journal back in 2008. It's a very fundamental test. So it's very simple. You have sensors, only 2 sensors, and then you impact it at both sides, okay? And then average the data. Okay? From there, you construct a relationship between the amplitude ratio with the depth to wavelength ratio. We normalize the parameters. So these are the curves. They show very good correlation. Okay? By taking the positive phase of the amplitude, negative phase of the amplitude, or by taking the average of positive and negative. All 3 phases show very promising results. And we, in the paper, in fact, we have proposed this method as one of the simple method that can be applied, okay, at the site, okay, to predict the depth of any surface grating crack. So this is one of the things. I mean, we have presented you two research. One is about tomography, another one is about radio wave. And I don't have the slide. There is another one which is based on the utilization of acoustic emission. We have acoustic emission research, and we have been trying this. Do you know acoustic emission? All right. Let me check. Acoustic emission is actually a passive technique, meaning to say that it's like a doctor holding a stethoscope. Okay, you place a stethoscope to the chest of the patient, you just listen to it. And you don't simply knock it right, you don't knock it or you don't damage it in order to generate some wave or vibration. You just put it and hear to the beating of the heart. So this is pretty much similar to acoustic emission. It is basically used to monitor structures. For example, bridges. Attach the sensors to the bottom surface of bridge deck. Then wait for the traffic to come. And you monitor it for example, a few hours, up to 24 hours. Collect the data. The data is in the form of wave, vibrations. And we carried out analysis. And we can tell from the waveform that we capture, we can try to analyze it and characterize the damage level, for example. So this is the basic principle of acoustic emission. These slides are basically about the integration. This is a very huge grant that we have managed to obtain in the University of Malaya. This is the so-called high impact research grant. And what we did in the proposal, the presentation of this, is that we try to appeal to the selection committee that although in the market we have a lot of different types of non-destructive testing as well as structural health monitoring techniques, but no one has actually tried to integrate different techniques in order to achieve a certain level of reliability as well as accuracy. So we focus on this one. We try to study different types of these techniques and we try to modify them so that they will match with each other in order to produce a more reliable assessment scheme. So these techniques can be basically classified into 2 types. The first one is the so-called global scanning or the monitoring techniques. So acoustic emission or maybe the fiber optic sensing falls into this category. It can capture the global behavior, for example, a structure or a bridge, the vibration behavior. So vibration testing is also one of the global techniques. So, but we couldn't tell exactly which are the where is the problematic spot. So maybe they will give you some indication. These techniques will tell you roughly there is some weak spot there, but we couldn't know how weak is the spot. What is the depth of the crack, for example? How deep is it? Or what is the orientation? So from there, we have to implement different set of techniques, the so-called local evaluation of assessment techniques. So the Rayleigh wave actually can be classified as the local techniques. We can focus on those problematic spots, just characterize the damage. So incorporating these different techniques require very extensive research and a lot of experiments, because we want to package it into a different methodology, a totally different one. So this involves instrumentation, okay, of the measurement system. system, how you attach the sensor, okay, how you generate the wave, how you do the monitoring, what is the interval, for example. And then after you collect the data, how you analyze it, okay, the signal processing. And then after you analyze it, you need the knowledge and experience to interpret the data. Okay? If you only know how to measure and how to collect data, you are not a qualified engineer, you are just operator. Right? So you need to have the knowledge. Knowledge comes from study and experience. So you need to know how to interpret. Based on the data that you have, you can tell whether the structure is good or not. If it is good, how good is it? If it is bad, how bad is it? How many lives, how many years left, okay, for it to service if you don't repair or if you don't maintain it. So I think I've taken a lot of time. So also we have a study in fiber optic sensing, the fiber breaking. You can check it out. And we have been working with Dr. Rafikong, and we are going to Thailand to do some actual measurement.
I will show some stuff.
Yes, yes. So we, in University of Malaya, we have the capability. Actually, we have been collaborating with the science faculty in the lab, whereby they can produce the fiber optic themselves, the sensors themselves. So cost-wise, it's very cheap. I mean, minimize the cost. And we will try to integrate fiber optic sensing with acoustic emission and with some other technology.